Okay, good morning all. Let us start today's lecture. Let me share the screen first. And we shall start with just having a brief recap of what we did in the previous class. Is the screen visible?
Yes, sir, it's visible.
Okay. So, as you all know, we have started with the third module and the second lecture, that is the previous lecture that we discussed. We discussed about the neural network representation, right? How do we represent a particular artificial neural network? So we had a system. We discussed a system called Alvin system, which was successfully tested. Let me take a laser here. Okay, so we discussed the Alvin system, which was actually a learned artificial neural network to steer an autonomous vehicle, right? And we saw how it was done. We saw an example how this system takes the input from the front-mounted camera here, and the system which is placed here is the responsible to give the direction in which this car has to turn, unless the human has to intervene, right? So there's just a programmer who has sit there, but having the how the system is behaving and when an interruption, if it required, when an interruption has to be done, right? So as I said in the previous lecture, the system was able to go at the speed of 70 miles per hour to a distance of 90 miles, right? So that was a remarkable achievement, and this is how the neural network represented. So we have three basic layers when we want to segregate. We have three basic layers, and one being the input layer. Second is the intermediate layer, which is the hidden layer, also known as the hidden layer. And third one is the output layer, right, where we get the actual output of our program, that is the decision. In this case, it is the decision to whether steer left or to take a right or to go straight or whatever. So the number of units in the hidden layer, the number of units in the output layer, they depends on the problem statement. But here in this case, in the Alvin system, as you can see that input sensor with 30 by 32 pixels. So that makes around 960 pixel image was given as the input to the system, right? And each pixel, as you can see here, let's say if this is pixel 1 and pixel 2, every pixel was given as the input to the next unit, which is the hidden layer. And of course, the output of the hidden layer was given as the input to the output units. So here in this case, we had only 30 output units, each unit defining some degree of whether the left turn or a right turn or straight ahead, right? So this is just a neural network representation of the in this particular case for the Alvin system. Now, here you can see there is a weight matrix or weight magnitude representation. You can see there's a diagram for all the 960 pixels here. But there you can see few white dots, few black dots, and again few bigger white dots, few smaller white dots, as well as bigger black dots and smaller black dots, right? So white here denotes that it is the positive output, right? The output that we are looking for, it's a positive output, and black denotes the negative, right? So this diagram here, this is the whole representation, the weight magnitude of the whole image, the initial image. But here what you see, a strip, a small strip or a stretched rectangular figure in which you have one line of dots in which few are white and few are black. So white denotes that it is the positive output, right? So you can clearly make it out here that the according to the system, according to the Alvin system, it is slightly recommending the left turn, right? So that was just a weight matrix of how, and in this, one more thing is that the bigger the dot size, that means the bigger the white dot or bigger the black dot, that means it has that particular pixel has the more weightage, right? Or that particular pixel has the more weight value. We will see what are these weights in order to segregate how these different weights are playing the important role here, right? And exactly opposite, the smaller the dot is, it has lower weight, right? So we'll discuss the same thing here. And as I said, the network structure for this Alvin is typical structure what we have seen here. But here in this case, we have individual units which are interconnected in the layers, and they are actually directed acyclic graph, right? So in general, artificial neural can have graphs with many different types of acyclic or even cyclic structure, or directed or undirected structured graphs, right? So that is what we have learned in the previous class, and we discussed that how backpropagation algorithm is the core algorithm behind this Alvin system, which is actually a cyclic feed-forward network system, and accordingly there are different types of other network systems also, which we'll be learning further, right? And we ultimately saw different appropriate problems which are suitable for the artificial neural network. So you can go through these. Right. So today's lecture is again very important aspect because we are going to learn the very core aspect of artificial neural network, that is the perceptrons. Right. So one type of artificial neural network you can say is this unit called perceptron. Now, what is this perceptron? Right? You must have already understood the term, or you must have already learned the term perceptron with respect to the biological aspect. But how do we define this perceptron in case of this machine learning is what we are going to see here. Right? So what is a perceptron? It is basically a unit which takes some values. Now, what are these different values? Basically, here perceptron they take vector values, right? The vector of different values, vector of real valued inputs. So, as you can see here, these are the different weights we have, right? Let's say we have this node x1, x2, and so on till xn, right? So every node here, which if you want to connect it to the previous example, let's say these circular shaded figures, they represent a pixel, right? So we have pixel from let's say x1, x2, so on till xn, and every pixel have a weightage value, right? So that is represented by w1, w2, and so on till wn, right? So this here, you can say it's a perceptron which takes a vector of real valued inputs, which are these values, and calculates a linear combination of these inputs, right? It calculates a linear combination of these inputs, and once it calculates, what is the output that we get? We either get output as 1, which output is 1 if the result is greater than some threshold. Now, what is that threshold? We will learn shortly. But let's say we have some threshold fixed depending on the problem statement, and above that threshold, then the value, the perceptron is going to give the output as value 1, and anyway otherwise will give you the output as -1, right? Now, what is that threshold is what we are going to see here, right? So as you can see here, this is very important diagram. This is a simple perceptron, how a perceptron would look like, right? In terms of this machine learning representation, simple representation. We have few sequence of inputs, right? These inputs are nothing but a combination of few values, right? Which is given as the input, and it is the summation of those input values are done together to form a linear, uh, a linear representation of it, a linear combination of these values. Just hold on. I think there are few more people joining. Right. So that linear representation of these values that we get will give you some output. Now that output can be 1 if it is above the threshold, and it will be -1 if it is otherwise, right? So let us go a little more into depth and see how do we get this, right? So you can see a simple diagram, a simple graph. You can say that, let's say if this is the threshold, if it is above the threshold, it is going to give 1, and if it is any way otherwise, it may give you -1 as the output. So that will be the value for this final unit, right? So you can connect now the input units, the hidden units, right, and the output unit. So when we give these values, different values as the input to the perceptron, right? For example, through x1 through xn, right? From x1 to xn here, we are simply giving a different values here to a perceptron, right? We have a range here. So to define, just to define the output, let us have this notation that O of x1 to xn. So that will represent our output, right? And the output, as I mentioned you, the output computed will be either 1, and if it is greater than the threshold, or if otherwise it will be -1. Now what is that threshold is what we are going to define here, right? So this linear function, the linear combination, as I mentioned, the linear combination is nothing but the summation of the values which we are giving, that is from x1 to xn, the vector of this value x1 from x1, x2 till xn, and the product of the weightage of that particular value, right? Just to show you here, for example, the value x1 and the product of x1 and w1 is the summation of these two values are come together to form a linear combination, right? So that's how we represent like this here. So initially W naught, if the value of x naught is producted with the value of W naught, and then it is summed together with all the other values that we have. For example, the number of pixels that we have. So just to give you an example, let's say in the previous case, in the Alvin system, we had 30 by 32 pixel image, right, as the input image taken from the mounted camera. So that makes it around 960 pixels, right? That makes 960 pixels for the input. So you can say these combination, these linear combination will go on up till 960 pixels, right? So W naught plus W1, X1, so on up till W 960 and X 960, right? So if this threshold, which is the summation and the product of these values, is greater than that threshold, it will return as the value is 1 or else -1. Now, what is this Wi and W2? I have already told you, these are the real valued constant which represents the weight, right? So these weights will determine whether the contribution of x1 or x2 or any particular value to the perceptron output, right? So, for example, let's say this W1 weightage is more, right? If this W1 weightage is more, then the contribution of x1 to this summation will be more, right? Quite evidently, right? So, if any particular pixel which has less weightage, right? I hope you can connect to the previous diagram. Let me show you the diagram. Yeah, as I said, the bigger dots they represent higher weightage, and the small dot they represent the less weightage. So as you can see here, there are these two white dots here. They are slightly more bigger than the other two dots, and as and when we go little right, you can see the dot has been become smaller and smaller. So that indirectly denotes that the weightage of these pixels are more. That means this degree, whatever the degree, let's say if it is something, let's say 82 degrees left turn, right? If this is 90-degree left turn, right? And if this is 90-degree right turn, then this will be around, let's say 82 degree, just a random figure that I'm taking, 82 degrees left turn. So that means that the weightage of this particular pixel is high, and that is the most recommended steering command or the direction the system will recommend to the machine, right, or the trained model here. So that weight is actually determines the contribution of that particular pixel, right, which is xi here, to the perceptron output, right. Now, one important thing to notice here is the quantity that is minus W naught, right. Now, what is this minus W naught? Minus W naught is the threshold that weighted combination of the input in this sequence, in that complete linear combination, like W1, X1, so on till Wn, Xn, it should surpass in order for the perceptron to be output as 1, right? I hope you get the point here. If the quantity minus W naught is a threshold. If that is the threshold, that the weighted combination of the input, this linear combination, must surpass, right? Surpass for what? In order for the perceptron to give the output as 1. So that will be the threshold. Right. So this representation of this threshold can be done in multiple ways. Right now, there are different ways we can represent this threshold. So just to simply give a simple representation, it is a simple summation of the values of weight as well as the value of the pixel, right? Which is nothing but Wi and Xi, right? So let's imagine that we have an additional constant, let's say X naught, which is equal to 1, and it is used to represent the inequality here. It will allow us to write the inequality. What inequality? The inequality that we saw here, right? The inequality that we saw here, that can be represented using this x naught by assuming that additional constant as x naught is equal to 1. Now the summation as it is shown here, summation from I is equal to 1 to n, and the product of these weight as well as values is greater than 0, or in the vector form represented like this. Right? So this is exactly the same representation, but this is in the vector form. So don't get confused in the exam when it is asked for the representation, any particular representation, whether it is in the form of summation or in the form of vector form, then these two representations, they both mean the same. Right? So vector form is more easier to remember, but summation format is better for understanding purpose. Right? So this is the vector form, and just for simplicity, we will sometimes denote these representation, this vector representation like this, right? So that means the output of these values, vector value x, is equal to the summation or sigma of uh, weightage, the weight of that particular pixel, and the value for that particular pixel, right? W and x. Right now, what is this summation of sigma here, which we have already discussed? Let's say we have a variable sigma y, then 1 if it is threshold, above the threshold, and otherwise it is minus 1. So this is our main threshold here. So that can be also represented in other ways. We will shortly discuss that. But the learning of the perceptron, right? How the question arises, how it is learned, how a particular perceptron learns, right? Of course, we have an input, we have few sequence of values which is computing via the linear combination in this case, and we are getting some output. But what is the learning of the perceptron? How can we say that the perceptron has learned, right? So a perceptron can be said to learn when it involves the choosing the values for these weightage, right? When it involves the choosing for those values for the weightage W0 to Wn, right? Now, how it can be chooses, how these values can be chosen. If you can recall the hypothesis space, right? We have a set of hypotheses. We have different varieties, different set of hypotheses. We have learned in the finders algorithm as well as in the candidate elimination algorithm, right? So the space H means the complete set of uh, different hypotheses, right? The space hypothesis space H of candidate hypothesis, different candidate hypothesis considered in the perceptron learning is the set of all possible real valued weight vectors, right? They are the real valued weight vectors. How can we represent this simple understanding of learning a perceptron? This is the simple representation, right? That is, the hypothesis space is equal to the weight vector, right? The weight vector itself, such that the weight vector belongs to some real value. Now, this representation is the real value, right? So this is how a simple representation of a perceptron uh, is learned, right? So when, let's say, when a simple question is asked, like, how can you say that a perceptron has learned, right? Or when you say that a perceptron has learned. So the simple answer for that is a perceptron is said to be learned when it involves choosing the values for the weights from 0 to n, whatever that weightage value is, W0 to Wn, and you can mention the representation here, which means that the hypothesis, the space, hypothesis space of the candidate hypothesis, that means the set of all hypotheses, considered in the perceptron learning is the set of all the possible real valued weight vectors, right? All the real valued weight vectors. So another way to represent is simple. Now, as you can see, we have replaced simple summation with a vector. Now, that means that we can also represent this notation like this. The output of a vector x is equal to 1 if it is above the threshold, or else minus 1 otherwise. What is this threshold? We have already seen in the previous slide. Right. So, any doubt so far? Anybody? Before we proceed ahead. There is a very important aspect of one of the ANN type, right? A perceptron. Perceptron is one of the ANN type, and understanding the perceptron is very important from the artificial neural network point of view. And artificial neural network as a whole is very important to understand machine learning. These are the core aspects of machine learning that we are discussing. So if you have any doubt, you can ask. The session is open for doubt clarification. Yeah, anybody, any doubt? I may have to randomly pick the people then. Yeah, Rahul,
No, sir.
no doubt. Anybody else? Rohan, please, any aspect that you have not understood, we'll repeat it again. There's no issues because these are very important aspects. We have to understand this if we want to proceed ahead, right? So if you have even a silliest doubt, please don't hesitate to ask. Even the same doubt can be there with one of your other friend, so it will help them to clarify as well. Please be active in asking doubts. You should always ask a doubt if you didn't understand even a simple aspect of it. And this subject is very important, and this topic what we are discussing right now is also very important. And the very core aspect is what we are discussing here, that is a perceptron, is all is very important again. Any particular thing which we have not understood, we can revisit that particular slide and discuss it again. Please respond, guys. Any doubt? Okay. You answers in the chat box. Others are always, as always, no. Fine. Okay, so moving ahead, let's get into more details about how this representation is very important. Why this representation, what that we discussed just now, the representation of a perceptron. Why is it important, and what is the motive of having this representation? What is the power of having this representation of a perceptron? Right. So representational power of a perceptron is what we are going to discuss now. So, in order to first represent, to define the representational power, why it is important, it is in simple terms. If I have to say, it is just to make the, uh, the classification or simply, the segregation of these whatever decisions or instructions or whatever output or result, whatever we get, right? To bifurcate those or analyze those output in a simpler manner. Right? So the better the representation, the better understanding and analysis will be there. Right. So we we can view this particular perceptron as representing a hyperplane decision surface. Now, what is this hyperplane? Uh, let's we will understand this one by one. Like, what is how can we view this perceptron, what we discussed just now, as representing a hyperplane decision surface. So let's say if I want to put it into a two-dimensional representation, right? Uh, there can be multiple dimensional in which we can put it. Like for example, there is no limit to it. I mean, there are so much to be explored. So we can have simply n dimensional space for every possible instances that we have, right? So instances are nothing but the points, right? For example, in our case, it can be pixel, every pixel, right? So that can be one instance. So that can be represented in n dimensional space, right? It can be three dimensional, four dimensional, five dimensional. Right now, there is no way that we can limit it. There is so much to explore. So, but let us start with a simple representation, that is a simple two-dimensional representation. How we can represent it into a hyperplane decision surface, right? So, as we have already discussed, the perceptron outputs one, right? For an instance, it can be any instance. The instance, for that matter, let's say the instance lying on one side. Okay, so what we are going to do here, we are going to draw a threshold line, something like a threshold line, and anything above that threshold line, one side of it, we are going to output it as a one, result is one, and the other side of the threshold will be minus one, right? So in other words, one will be for the instances lying on one side of a threshold value, one side of the hyperplane, right? Now this hyperplane is our threshold, and minus one for the instances on the other side, right? So the equation of this hyperplane, what does the equation becomes? It simply becomes zero, right? How? Because it is a neutral value, right? Or hyperplane is nothing but an intermediate value. So whatever we are defining that particular hyperplane, above it or one side of it is 1 and other side of it is minus 1. So of course the hyperplane has to be 0, right? So it can be represented using this vector representation form, that is a vector product of weight as well as the value x equal to 0. Now this is for the hyperplane, right? Please note it is for the hyperplane. Now, some sets of the positive and the negative examples. Now, what are these positive and negative? You can relate it to the previous example, that is pixels. There were few white dots which were representing positive values, and there were negative values which are represented by black dots, right? So, some sets of these positive as well as these negative examples cannot be separated, right? It depends. There can be a representation in which simple segregation cannot be possible, right? In few cases, but if that separation can be possible, then that separation can be called as a linearly separatable or linearly separable set of examples, right? If we can clearly segregate these positive examples and negative examples, right, then we can call it is a linearly separable set of examples. But there might be many cases when set of those positive as well as negative examples cannot be separated by any of the hyperplane, not just a simple straight line, but any of the hyperplane. Right. So just to give you a representation of it, let me show you this using a diagram. Right. So let's say we have these two types of representation, representation A and representation B. So this is a simple surface representation, decision surface representation for a two input perceptron. It has two inputs and it is going to give a output. Right. Now in first scenario, in the first case, as you can see, there is a hyperplane drawn, right? The reason why we were able to draw that hyperplane is because there is a facility to separate positive examples from the negative examples, right? So in figure A, as you can see, the set of training examples and this decision surface of the perceptron can be classified easily and correctly, right? Because we have positive output here, positive example here, positive example here, negative example here, here, and here. So we can definitely draw a hyperplane or a separable line which can segregate or classify these training examples. But in other case, in the second case, that is figure B, you can see you cannot form any hyperplane or any line which can actually segregate all the positive examples and all the negative examples, right? So it cannot be linearly separable, right? That is, it cannot be correctly classified. It cannot be exactly classified whether uh, what to be whether it has to be positive result or a negative result. So it cannot be correctly classified by any straight line here in this case. You take an example, if you draw like this, you have one positive case here, right? Or if you try to draw, let's say like this, but still you have positive, negative here, positive, negative here. So likewise, you try to draw any straight line, but you cannot correctly classify the positive examples as well as the negative examples separately, right? So this is the decision surface representation of a two input perceptron, right? So input here is the x1 and x2. The more the input, it will be more complicated. So this is just the two input. Input here is x1 and x2. They are the perceptron inputs, and positive examples, which are, as you can see, are denoted by positive and negative by negative. Now this is a simple, hyperplane representation of perceptron, right? So I hope this understanding of what can be the power of this representation or the representational power of a perceptron, why it is important, and how does it play a role in better classifying. Now, in brief, understanding again, just to put it in a nutshell, if we have a better representation of a perceptron, it might result into a better classification. And when we have a better classification, a better as well as a correct classification, then we can land up to a decision which is a clear decision, right? There will be no ambiguity in the decision. For example, if you are driving, we'll take the same example, that is Alvin system, and if the representation of the perceptron in that case, in the case of Alvin, can be correctly represented, and it will be represented in such a way that the positive examples can be clearly classified with the negative examples. Then in that case, the system can represent this hyperplane in a very correct manner, which will result to a clarity in the decision, right? Whether it has to be a positive or a negative, whether it has to be a left turn or a right turn. If it is left, how much degree, that also accuracy, and if it is right, how much degree right, and so on. If it is straight, it's simply straight. So neutral. So that hyperplane value, that itself will become a neutral value or a straight command, straight decision. Right. So the clarity of the decision, if there is ambiguity, then the system might fail. Right. In case of, let's say, if there is an obstacle in the left side, but it is not clearly defining that you have to take a right, and it is giving you wrong input, the degree of turning the right direction is not clear, then it may happen that whether the system can directly collide, or may slightly hit the obstacle. So these are just the possibilities that I'm giving. So that is the importance of different representations, or the representational power of a perceptron. So I hope you understood the point here. So anybody having any doubt with respect to this representational power of perceptron? Let me show you the diagram again, so that if you have any doubts, you can ask. Yeah, anybody, any doubt in whatever we have discussed so far? Not just today's lecture, but whatever we have discussed. So fine. So if there are no doubts, then there's one more thing about the perceptron, that is the perceptron training rule. How, what is the rule to train a particular perceptron is what that we are going to learn. So using those weightage, those vector metrics, the vectors and the weight metrics and those things we are going to learn, and how can we manage if there is a deviation or a slight change, or what can be error that can be called, which can be called as an error, how to deal with those, and there are different ways to do it. So that is what we are going to learn in the next class. So if you have no doubts, we shall conclude the lecture here. Thank you.